Hello grade 11s. Today we are dealing with the potential energy and covalent bonding curve. Basically, this graph explains how covalent bonding actually occurs. You will find it under the bonding section of your exam guidelines, under interpreting a graph of potential energy versus the distance between two nuclei for approaching hydrogen atoms. So that's where you will find it in your guidelines. When atoms form covalent bonds, they share electrons. But why do they do this? To understand, we look at energy, specifically potential energy, as atoms approach each other. This is the graph we're going to be working with. On the x-axis, you have the distance between the nucleus. So this is one atom and this is one atom. And the black dots represent the nucleus, which is positive. And the y-axis represents potential energy. This is a zero line, which represents the point where there is no potential energy. And you'll see that the level of energy decreases as the atoms get closer together. So the distance, as the distance between them gets to zero, okay, they are actually moving closer together. So we read this graph from right to left. Imagine two hydrogen atoms far apart. At this point, the atoms are way too far to attract each other, and when they are far apart from each other, there's no interaction, there's no attraction, and there's no repulsion. And so the potential energy is very, very low, and it's close to zero. So this is a zero line, and the potential energy graph is very close to zero at this point. Now at point 2, we have something called electrostatic attraction. So there is a force of attraction between this nucleus and this atom's electrons, and this nucleus and that atom's electrons. So as the atoms move closer towards each other, the electrons of one atom are attracted to the nucleus of the other atom. This attraction lowers the system's potential energy, and this is the start of bond formation. The potential energy decreases as the atoms come closer together. This is shown by the downward slope. The lowest point on the graph is called the bond length, and it is representing the state of the most stability and the lowest energy. Let's look carefully at all of the electrostatic forces at play. The first one is that there is attraction at this point, this minimum point over here, between the positive nucleus and the electron. Then there is also repulsion between the two electrons of the opposite atoms, and also there is repulsion between the two nuclei. This is shown by this diagram that shows the nucleus of one hydrogen atom and the nucleus of another. And then it also shows us the electrostatic forces at play. So there is repulsion between the two nuclei. That is one of the electrostatic forces. Then there is repulsion between the electrons that are being shared because they are like charges. Then there is the attractive force between this one's electron and this one's nucleus, and there's another attraction between the other hydrogen atom's nucleus and the other hydrogen atom's electron. So there's a balance of forces, okay? And that is what causes this to be a chemical bond, because they are not too close and not too far. The repulsive forces balance out the attractive forces, and this creates a stability. The energy difference between point 1, this point, and point 3, which is the minimum point, is the bond energy. It is the amount of energy that is released when the bond is formed, and it must also be absorbed in order to break the same bond. So remember that ballerina dance, energy is needed to break a bond, and energy is released when a bond is actually formed. And then this distance over here is the distance between the two nuclei, and that can also be read off the x-axis of the graph. So this graph specifically is for hydrogen bonding, but you do get the same type of pattern for any covalent molecule. And for hydrogen specifically, the length is 74 and the bond energy is 432 kilojoules per mole. If the atoms move even closer to each other, so they formed a very stable bond, everyone's happy, we're keeping our space, but we're still together. But sometimes people can get in your space, too much in your space, and atoms experience the same thing. If the atoms move even closer, the nuclei start to repel each other with an increased level of repulsive force. This increases the potential energy very sharply. So this is the steep rise on the graph. And that is why the system's energy will increase and force the atoms to 0.3 again, because the lower the energy, the higher the stability. And this point is where the atoms are the most stable, not too close and not too far. So the deeper the energy well, the more energy is needed to actually break the bond. That means if the energy well is very deep, you need a lot of energy to break the bond. And the bond length is where the system has a minimum level of energy, which is the most stable, and that is where the bond, the covalent bond, actually forms.